let's welcome our next speaker, who is Marco Agus from Hamad bin Khalifa University. He was previously a researcher at KAUST in Saudi Arabia. And today, if technology allows us, Marco will talk to us about AI and visual computing for histopathology images, which we started a bit yesterday, introduction. So we are really looking forward to your lecture, and I'm really intrigued to hear more. Thank you for.
So thank you, Katerina, and thank you to all of you for inviting here. And good afternoon to all of you. It's nice to see, the future of the visualization community more or less here. And today I will try to give a sort of primer, short introduction about a topic that it's like we started to touch a few years ago in Qatar, in my university, and it's like it was considered of high interest for Bara when she invited me, because it seems that our community, some groups are touching it, but some other groups, is not really so much represented in the field, even if it's really, really important. And now we will see in the course of this presentation what are the challenges and what are the current problems in the field, especially in the world, and especially from the domain point of view. So before starting, just a little bit of advertisement. Like when you go to the theater for a movie, it's like, there is some advertisement. In this case, I will try to advertise about, the country where I currently work. It's Qatar. And, without, spending too much time, is just, I wanted to, to tell you that it's like the FIFA World Cup is coming. It will be a really big event in my country, and probably it will affect also our productivity, because I'm expecting that during that month, it will be very difficult to do any kind of academic activity. In any case, if you have a chance to visit it, will be for sure a lot of fun. And you will have also the chance to enjoy a very nice weather in that period, with a little bit less of rain that you can expect here in the center of Europe. And, so you are invited to join us and to enjoy the country. Then the second advertisement is related to the university where I currently work, that is called Hamad bin Khalifa. Is part of the Qatar Foundation. It's a very young university. We started like 12 years ago, and especially our college was founded like 7 years ago. We have around 60, I don't see here, around 75 faculties now, and we have various graduate programs, only one undergraduate program, and the focus for what concerns research is related to national thematic areas that are related to cybersecurity, artificial intelligence nowadays, and also precision medicine. That's why, also we started working on histopathology. So, and for what concerns my current activities and also the activities of my colleagues, we just funded, we just, established a very small lab that we called the Idea Lab, because we tried to join together the expertise of two visualization scientists, that it's me and Dr. Jens Snyder, and two faculties that are working on computer-human interaction and accessibility. So we called the lab Idea Lab. Hopefully, we will have a lot of ideas, and I will try to, to do some sort of synergies between the different fields. We organized a few small workshops that we call VSky, for trying to join together visualization and computer-human interaction. And for what concerns the research interests, we try to work on interactive visualization of complex data. And especially me and Dr. Jens, we are coming from scientific visualization, so we try to do something related to volume rendering. And then currently we are started to investigate machine learning, especially for application to 2D through 3D problems. We have a project in which we try to use machine learning to try to infer information about indoor environments. And it's like this was quite a successful project in which we developed various models for doing this sort of operations in indoor environments, like automatic emptying of a room, that is something that we will present soon in a ISMAR conference. And also for trying to infer the depth signal for performing, for creating various kind of augmented reality applications for virtual staging. So it's sort of a hot topic. And also, of course, medicine, biology, and so on. And but today is like, the topic of our talk will be related to digital pathology. And at the beginning, I will try to show a little bit primer about the history and the various, part of digital histology. I will provide an overview of the data resources that you can find online. That is also the resources that we currently use for our investigation. And then I will try to show a little bit of the current role of artificial intelligence and visual computing. I will showcase a little bit of our contributions, small contributions, because we started very recently. And then I will try to delineate what are the challenges and the future directions. Okay, so this for starting, I just mentioned what are the the new disciplines that are that's like they are arising. Is like recently related to pathology. One is called computational pathology. There's some term that was probably created maybe 5-6 years ago, and it's related to the connection between the various computational and processing methods that you can have applied to images that are used for quantification and for creating effective tools for analyzing specimens, tissues, and so on and so forth, helping the diagnosis process from pathologists. And very recently, there's another new term, a new discipline is called precision pathology. So usually as a part of precision medicine that is connected to pathology, in which there is a big integration of data, and with a target of try to get a personalized patient care, and instead trying to provide as a more effective tools for treatments and so on. It's like a very recently big initiatives, especially in the big hospitals in the United States, like Sloan Center of John Hopkins and so on. They're starting to creating biobanks in which they are putting together a lot of different kind of data, like digital slides and metadata related to patients, in a way to drive a sort of synergy between the various technologies for managing to get towards a more personalized way to treat the patients and to obtain a diagnosis. To get into that, it's like there was a long process. It started more or less 20 years ago, and from a project that was called the virtual microscopy, in which there was the first time it's like the people tried to digitalize the glass slides, and after this successful project that was created by the John Hopkins University, the University of Baltimore, the companies realized that the high potential of this kind of technology, and nowadays you can have a plethora of digital scanners that are with that can provide a digital representation of glass slides. They're called wall slides at a very high resolution. It's like 40 pairs. So with this kind of technology, you can obtain easily image that can reach even gigapixel size. And for using this kind of image, you have different kind of ways to treat the data, for storing or for streaming, and then for interactive visualization and annotations. And since the advent of, and the creation of the first prototypes up to the first commercialization of the various devices and machines, so like there was a lot of literature and a lot of groups, it's like investigating the potential of these technologies, and it's like with different kind of studies to try to figure out if the digital technologies related to Walls light imaging could provide, it's like a way for being used as a primary diagnosis tool. And it's like after a process of 20 years that for the medical field is not really that long process. It's like the Food and Drug Administration in the United States decided to accept the Walls light imaging, so the digital pathology methods as a tool for primary diagnosis. As you can see here, there was like in this table, there is a sort of overview for the different kind of subspecialty of what is the concordance for what concerns the accuracy in diagnosis between, the standard way for performing analysis of microscopic images and the digital way. As you can see, is like in most cases we are closer to 100% or at least over 90%. So that's, that seems that, the world is evolving to use digital technologies for managing slide and diagnosis. And so what are we getting after? And it's like we will see in next slides, but it's like now let's get back to try to figure out what are the problems that pathologists needed to face when they are dealing with the analysis of virtual slides. And it's like the pathologist has the task to try to figure out what is happening inside the slide by doing a visual exploration at various magnification scales of different parts of the wall slide image, from the large scale in a way to try to recognize what parts are containing, the lesions like or the tumors, up to try to figure out image-derived features, and up to try to figure out and to count cells and determine the various morphology features in order to figure out what are the problems. So usually here you can see it's like in an analysis session that in 5 minutes, it's like a pathologist change the various zoom levels for performing different kind of operations. And after this kind of operations, that it comes out with a diagnosis report. And it's like normally when it comes out with the diagnosis report, this is the final answer. This is, the final decision. So it's a sort of high responsibility decision for the pathologist. So in general, it's like you can figure out that since there are many kind of diseases, many kind of molecular processes happening inside one tissue, this is a really tough job. And also you can imagine that it's like, and this job has high responsibility. And I discovered also that pathologists in the world, they are not, there are not too many pathologists in the world. The bad point is it's very tough job. The good point is that I mean, at least for our experience, they tended to be more interested with respect to the standard, physicians to use easily new technologies. That's why they migrated to digital technologies faster compared to other disciplines that are things. And for what concerns also the task and the workflow of a pathologist, it's like it seems to be a very tough job and it needs a lot of experience, a lot of knowledge. But luckily, they have also a lot of guidelines and a lot of protocols to follow for managing their task. So it's like there are public domain resources like the College of American Pathologists that provide guidelines and protocols for performing accurate analysis and for the different kind of disease in the different kind of cancer. And for example, here this is one of the most popular protocol related to the breast cancer that is based on a grading protocol that is called Nauticam histological, in which histopathologists need to try to evaluate different kind of features like the formation of tubules or the morphology of the nucleus of the various cells, or also to count how many cells they subdivided within mitosis. And then they have a sort of guidelines for scoring this kind of features, and the final score is determining what is the severity of the disease and what is the aggressivity of disease. And these kind of protocols, they are normally quite accepted. They are normally used, and they are also present in a sort of reports that they can be used. They can be used for having, it's like a final report about diagnosis. Another example is related to prostate cancer, in which, the pathologists need to evaluate what is the clustering and, it's like the distribution of the tumor cells and the shapes in a way to try to evaluate how do they cluster together in a way to try to distinguish various architectural patterns. And according to them, they have a similar way that's called Gleason score to rate and grade the prognosis and to rate the aggressivity of the cancer. So it's like even with this kind of protocols, I mean, because like there is the big issue is that there is a big shortage of pathologists in the world. I mean, this map is like was created like maybe 2 weeks ago from by the director of the digital pathology in Japan, who made a big survey to try to figure out what is the status of pathologists all over the world. And it's like he recovered this kind of information that a part of the North America, probably Australia, and maybe some parts in Europe like UK, the rest of the world is experiencing a big shortage of pathologists. And as you can also imagine, it's like, there's according to, that's like the presence of pathologists is a sort of indicator of the quality of the health system. And you can also figure out that it's like the number of pathologists that are present in the various parts of the world, they have a very high workload, sorry. And it's like, it's like the high workload means that it's also the quality of the diagnosis and the quality of the outcomes could be lower that could be expected. So it's like you can imagine that it's like the companies, especially the medical companies, they are perfectly aware about this kind of problem, and there is a big pressure, to speed up the usage of artificial intelligence in the workflow more than in other fields of in medicine. And that's in fact, it's like in last year, there was a big milestone. There was one product from a Page company related to the prostate diagnosis that was first AI-based pathology product that was approved by the Food and Drug Administration for clinical use. And after the approval on September 2021, in September 2022, there were the first results of the clinical validation. And that's the results showed that is like there was a high improvement with respect to standard way to perform diagnosis, but it's like I would say not as high that it could be expected with the usage of artificial intelligence frameworks. And so that's more or less, the status currently. So you can imagine it's like artificial intelligence in the future will be, will be more and more considered for the digital pathology workflows. For what concerns data, it's like the most important, for say, resource that you can find actually for getting data for digital pathology, especially for making molecular studies and for genomic studies, is called the Cancer Genomic Atlas. That is a huge project started maybe 15 years ago. That's containing 2.5 petabytes. That is targeting 33 different tumor types, and that is used extensively for trying to figure out similarities and differences between the various kinds of cancers, and to use this kind of information to develop therapeutic strategies, and also for classifying and for recognizing new subtypes of tumor and creating a different therapeutic target. And recently also is like for what concerns public domain data, this data set that also we are currently using. It's called PanNuke dataset. It is a data set in which 19 types of cancers that are represented, and is containing a semantic segmentation mask of various patches of wall slides, and it contains more than 200K labeled nuclei, and it can be used for for benchmarking, for creating a different kind of models, for creating various kind of artificial intelligence frameworks. And finally, it's like for what concerns data sets, for all of you who could be interested, it's like regularly in MICAI and Kaggle, they release a challenge that are, in which various kind of data for different tasks related to different kind of protocols, they are released, and they can be used for, for investigation, for developing models, and so on. So in any case, the community, computer vision community, machine learning community, is very active in this field. And so it's like things are improving day by day. Then, for what concerns the way which deep learning can be used for the digital pathology workflow, you can imagine easily that it's like at the end of the story, the most important usage that you can have for deep learning is to try to reduce the effort and to speed up the workflow of pathologists or researchers. So it's like at the end, what is needed is to try to get automatic ways for performing time-consuming tasks. That would be detection or segmentation or extraction of features at various scale, or in our case also for creating automatic annotations that using that you will see next minute. And most of, especially what is of interest for pathologists is to have task automation related to protocols. So for what concern the segmentation, the classification, here I will not provide, a long overview of hundreds of methods that you can find in the literature. I just showcase a little few that they're considered the most, the most performing and the most popular in literature, and they're related to segmentation and classification. Christina mentioned the UNet in the previous talk. That is one of the popular ones. Another one that is quite recent is called Overnet. That is still a customization of encoder-decoder network, in which the decoding part is branched in 3 parts, in which there is one part to try to figure out where are what are the pixels composing the nuclei. Another part is more specific for the nuclear classification. And then the secret of this network is to figure out a sort of gradient map for the horizontal and the vertical feed that is helping both the segmentation and the classification. In any case, if you are interested, it's like you can find also the source code of this model online. It is pretty much used. And then it's like just another example that is this is very recent. It is a sort of trend for the computer vision and the artificial intelligence community is to try to put together NLP, natural language processing, and convolutional neural network in order to improve a vision task. And that's obtained by putting together, by combining, and by inserting the features that you can have by analyzing the text, and to create a sort of help for convolutional neural network for creating a better attention and a better discrimination of pixels. This is a sort of, this technology is currently used, probably I will mention even the last slides, for generating even images, because I don't know if probably you heard about the DALI framework that is able to generate image by textual description of what is the content. And this method is a sort of a version of this kind of technology, but used for segmentation. And so it's like this is a very small overview of what are the current trends for what concerns the usage of this kind of models. I think that today you had a lot of talks talking about the visual analytics and the visual analytics workflow, how to put together visualization data models and to put the operator in the loop. I would like to mention here only that at the end of the process for the clinician, the most important thing is how to get knowledge. So how to create reports in a fastest way. And I will mention also that it's like for digital pathology, our community did not dedicate too much into this topic. So most of the works that I will present, they were mostly done by the University of Eindhoven or Van Wyk group, Alberto Corvo, and started from the pathology applied to breast cancer. So he started by creating a visual analytics tool that were able to help pathologists to create the Nottingham score grade for breast cancer. And the first system he created was a sort of transparent system in which the pathologists used the normal workflow. So it's like the normal examination process. And in the meantime, some system was tracking the operation of the pathologist and tracing the diagnostic work in a way to create a sort of a form for the report with image, with information of what the pathologist was doing. And in this way, the pathologist could have a sort of highlight of what he did, and that he could add his annotations and additional findings and so on. So it's a sort of automatic reporting based on tracing the activity of the pathologist. They increased and enriched this kind of approach by creating a protocol-based approach. So just they replicated the tasks that are included in the protocol for the breast cancer for creating a specific dashboard in which they added various models and integrated in computer-aided diagnosis systems in a way to provide a more comprehensive toolkit for performing automatic diagnosis. And finally, it's like this is very recently, it's like a expanded the system for creating a sort of framework that was able to work with cohorts. So to put together data from different patients, creating constructions, and creating a system that was able to formulate hypotheses and perform a sort of cohort analysis. So with the provenance graph and the various toolkits for trying to figure out and to try to get and to answer some kind of hypothesis related to the aggressiveness or the presence of different kind of tissues that could be mapped to sort of outcomes that in the case was the survival rate. And finally, this is sort of also very recent work. This was from Harvard group that is more related to other kind to high dimensional multi-channel image, in which this kind of images are containing up to 60 plus channels. But this kind of technology is a cutting-edge technology, so it's not available in the hospitals, as it's used more on research in research field. And in this case, in this kind of system that is called Facetto, users can perform a semi-automatic analysis of these various cell types, can integrate various supervised and unsupervised models, and they can also have tools for performing feature exploration like dimensional projection and so on. And finally, it's like, it's like I will mention briefly about our, our contributions that's like last few years. It's like the one is related to a geometric framework for trying to perform analysis of nuclei that is using automatic segmentation to extract the various nuclei, and it is creating it's like a robust descriptor that is based on discrete differential geometry. So it's based on the analysis of curvatures, and it can be used for integrated in various in models, in classification models, together with other descriptors, or for performing morphology analysis together also with dimension reduction schemes. And this framework is based on the extraction of contours of the various cells that you can obtain by automatic segmentation. In our case, we use the UNet. And then after some processes for smoothing and resampling, we compute the discrete curvatures by using discrete differential geometry, by incorporating the computation of osculating circles for vertices and edge. And from these coefficients, curvature coefficients, we can extract energy coefficients by performing Fourier analysis. And these can be used for the various tasks, or put together with other descriptors for trying to perform automatic classification, or can be used for automatic morphology analysis of the various cells. And then it's like you can use it also for proofing the quality and accuracy validity. So it's a sort of a framework that you can incorporate in a visual analytics system to support the pathologist when it's needed analysis of shape of nuclei. And it's like what we tried when we developed this framework is our goal was very ambitious. We wanted to use it for automatic classification. So we directly targeted PANUC, and then we discovered that the performance was poor. It's like we discovered that even with the composition of other features like foreign images obtained with autoencoders or other kind of features, we could reach maximum 60% of accuracy on the PANUC. So it's like a sort of we hit a wall with the engineered descriptor. That's why we decided to move on pre-trained the convolutional neural networks, and we tried with transfer learning. And then it's like with transfer learning, with some tricks, it's like now we are currently on a PANUC on accuracy of 85%. And that's something that our student will more or less describe in detail in this CDM on Friday. And it's a part, of our current framework that is for creating automatic visual annotations. In this case, it's like we decided to skip the segmentation, the automatic segmentation part, because we were more focused on detection and the classification. Also, it's like for speeding up the automatic annotation, because the detection models can be order of magnitudes faster than segmentation model. And it's like in this framework, we propose also two kinds of annotation. One is based on the single cells, and the other one is based on density analysis. Now I will show you now. And for what concerns the various, part of the framework, it's like I will briefly tell you what is the composition. We use a YOLO model for performing detection, and it's like we boost it by incorporating and by using a generative model that's called Histopathology, that is for improving the recognition of nuclei. And with this kind of model, we are now ready, able to have it's a detection rate that is around more than 80%, 84%. And the same model provides us an accuracy of 80%. But since we were not happy about the weighted accuracy on the PANUC model, we decided to incorporate an additional classification model that we created by using transfer learning with EfficientNet, and also we tried ResNet and SqueezeNet, and with other tricks like radial blurring, or also by using the bounding box that are obtained through the YOLO model. We were able to reach more or less 85%. And then it's like we used also GradCam, that is a class activation map visualization method for figure out what are the salient regions in the image that are used for prediction, for the class prediction. And we incorporated all these models in a framework for creating automatic annotation of wall slides. And it's like currently we are creating our annotation in form of GeoJSON format that can be imported in standard visualization, standard viewers and open source viewers for digital slides like QPath. And as annotation, as visual annotation, we provide two kinds of annotations. One is the bounding box of the various nuclei with indication of the probability of being part of a class, and also the color related to the various class. And also we provide density isocontours. We compute by using kernel density estimation, and in a way to create a sort of density map that at a high level can provide the pathologist the way to distinguish the most important features, and especially to try to figure out immediately what are the areas in which there are, there is a sort of contraposition between the neoplastic tissue and the inflammatory tissue and so on. So it's like, with the first qualitative sessions with the pathologist, he was particularly impressed by the fact he was able immediately to find, especially the area where there is inflammation reacting to the neoplastic tissue. So it's like we realized that probably we are in a good path for providing something that can be of interest for pathologists. So we will in the future also explore this area by also integrating topology analysis like mosaic complex and so on. So this is more or less the current status of our work. And actually we are able to provide provide annotation of whole slides in times that are more or less manageable. So we are able to have a full annotation in or time order of minutes or tens of minutes. And also we started the sort of analysis of the image contained in the TCGA, in the Cancer Genome Atlas. And we still have some issues for what concern the comparison between the metadata reporting the various percent of the various cells together with the one that we are obtaining. But that's also related to the fact that the PANUC is containing only some part, some portions of the cancers that they are representing the TCGA. So we needed to make more extensive analysis to realize what is on and what we can get with this technology. And finally, for future work, it's like we are collaborating actually with a pediatric hospital in Qatar, Sidra, and it's like and in this hospital, the pathologist, our pathologist is expert of a particular kind of tumor that's called Wilms tumor that is a particularly aggressive tumor, especially for youngsters. And in this hospital, there is a collection of a few thousand cases that are still, is like analogic slides, so they need to be digitalized. So in the future, we're starting a project which will provide, we will scan, label, and proofread these slides, and then we will try to, to follow the path indicated by the University of Eindhoven for creating protocol-based visual analytics system. And finally, it's like, just, the future scenarios. So I show you, and I mentioned about the fact that it's like, now it's realistic to have artificial intelligence frameworks that are able to create image with the textual description. And it's like, what could be a science fiction scenario is to have something that is taking as input the protocol guidelines and a description, and using AI for creating a custom dashboards, including models, including toolkits, including methods that are speeding up and managing the path for the workflow for pathologists. So I don't know, it's like that's more or less all. Even it's like as take-home messages. It's like, as usual, when we have a multidisciplinary projects, it's very important the communication between like computer scientists and the domain scientists. In this kind of a field, there are many challenges, and there are some issues. And one of the issues is the standardization of image formats, because there are many companies providing tools and devices, so it's very difficult to find a standard format that can be valid for all of the workflow. Also, the technology transfer is very important also to have something that can be used at large scale by the pathologist. In any case, that's more or less all from my side. I have, of course, in any case, persons to thank. It's like, the collaborators that are in Sidra, in KAUST, and also in CRS4. And of course, our students that do most of the job. So thank you for the attention. If you want to contact, it's like these are the contacts of me and my colleague Jens Schneider, and I'm ready to answer your questions.
Okay, thank you, Marco, very much. Hey, do we have any questions for Marco? I think Jan actually had one, so you can go ahead.
I was actually wondering, you have mentioned that there is a lack of clinical pathologists, and there is a need for them to replace this gap with the AI. But I was also wondering, since you mentioned that these pathologists have some legal binding to their patients, whether the legal system is already ready for having AI as in the in the production settings, in the clinical settings, because it was just recently then FDA allowed us to use these tools.
Okay, it's like I would expect that it's like it's like even when I mentioned about the FDA that was accepting, it's like the first AI tool based for the prostate cancer, the phage prostate cancer, I still think that is a sort of, a sort of tool in which at the end the pathologist will take the final decision. So the pathologist will always be in the loop until, at least I hope for the next 10 years. So, it's like this kind of, even in case, let's suppose that we have the worst case scenario of that you need to analyze a biopsy from Africa, and it's like needs to go to United States or to some and you need to use some AI tool and AI framework. I'm expecting that there should be some pathology taking responsibility of the decision, as like just to mention it. That's it.
Yeah, and should we also make responsible the programmers if they include the bugs in their applications? And then, the pathologist actually didn't had the chance to catch it, but there was, a mistake in the coding session. So maybe the guy who actually programmed it should be responsible. What would be your take on this?
I mean, it's like for what concern, it's like who is responsible of the usage of AI? It's like I read something in past related, the white papers for the European community that they were more or less created for, for autonomous driving, and but for the medical application, I sincerely don't know what will happen in the future. Who will be responsible if the guy is creating the AI toolkit or the pathologist using the system?
Okay, any more questions? If not, let's thank Marco once again.
Thank you.